Okay guys, it's time to continue. Once we're finished with shaft design, we're actually ready for an exam. Now that's not yet, don't panic. You guys are working on tolerances and bearings, right? I think that was the last thing we had before shaft design, wasn't it? Okay. So your assignment from today will be shaft design, which will get us through next week. So you'll turn in your shaft design, individual design projects by 11:59 on Thursday next week. Okay. And then after that, we could potentially have an exam. In fact, let's see, according to this, we have an exam coming up on the 11th, which is next Tuesday, but that's not going to happen, obviously, right? Because I want you guys to be able to turn in your shaft design homework, get it back. So my guess is we'll probably have an exam about the 20th or so. About 2 weeks from today should be our first exam, yes? You won't be here that class day. We'll have something where you can take it beforehand, say Wednesday or something like that. Okay?
Will we have a review?
A review day. I usually don't have reviews here. I think I might have some sample exams I can post. So remind me, I'll look and see if I've got them. Because I know how helpful those are. And I certainly don't mind posting them for you. And like I said, I am pulling hard. I'm trying to get through this material and get us to the point where we're designing stuff and building stuff, and not at the very end of the semester. I really want you guys to have time on the project before the end of the semester rolls around. So one of the things we're going to do, once you get belts under your belt, right, as well as chains, we probably at that point I'll start giving you time to work on the project. And this will be pretty structured. It's going to be time in class. And I don't expect you to just leave. What I expect to do is meet with groups individually and see how you're doing and help you and give you some hints and tell you what you need to do next. Okay, so make sure you meet your group members because the project is coming up on us pretty quickly. What else? There's something else I wanted to tell you. Oh, I turned on a new learning module. It's belts and chains. We're not going to slow down in the course material. So belts and chains will be the next topic, and it's kind of funny over here. We've got drawers with gears and bearings and belts and chains. Someone over there thought they were humorous and added whips to the belts and chains drawer. Who says engineers don't have a sense of humor? Okay, so anyway, I haven't removed it just because I thought it was funny, and somebody else would probably just put it back. Anyway, so let's talk about belts and chains, but not whips. Inspiration. Genius is 1% inspiration, 99% perspiration, which is why engineers sometimes smell really bad. This is our demotivational poster for today. I like it. All right, belts and chains, of course, are ubiquitous, just like fasteners, just like frames, just like shafts and bearings. These are all over the place. Probably you fell in love with mechanical engineering when you saw some of these things. You thought, man, that's cool. I can see how that works. I enjoy that. Well, there are many different types of belts. Now, these are some belts that are in use from Professor Dew's experience. As I said, I've designed a lot of small-scale stuff. He, on the other hand, is at the other end of the spectrum, has designed a lot of large-scale stuff. And so this is a very large vat that is supposed to shape the parts that are inside of it for whatever process they're going through. And so you'll notice the way this is designed, we're going to concentrate on the drive unit itself. This is one side of the drive unit. This is looking at it from the other side. So here's the motor that's down low. Here's the motor up high. And there are two separate belts. You see one belt here and another belt here. Now, you can't tell it very well from this photo, but these belts are basically multiple V-groove belts. Okay, that's what they are. So there's no synchronization there. On the other hand, the belts that run up here off these pulleys, now it's kind of confusing, but this pulley is designed to be on this side. The shaft runs through, comes out on this side, and goes here to a synchronous system. Why do you think they have that? Because, I mean, the shafts don't go from here. The shaft power goes in here from these motors, and these shafts, well, one connects up here, and the other one connects down there. Why do they have these? Almost.
Timing?
For timing, that's why. You see there are weights out here that have to be in time. You want the shaking forces in one direction to cancel and then the other direction to add. If you time the weights properly, you can make that happen. If the two motors get out of time with one another, then one weight will be driven out of sync with the other one. It won't shake the way you want it to. And so what this does, this box here must have gearing inside of it that prevents the shafts from being out of time with each other. Because you've got synchronous belts, and synchronous belts are what you probably call, timing belts is probably what you know them as if you've ever done any automotive work. Okay, but synchronous belts have teeth in them so that, unless a tooth is jumped, timing can be maintained. Okay? So there's many different types, and those are just two of the types that are available. This must be the setup before it was painted. Either that or this is a similar but different setup. You can see the same idea here. This must be a different, because this one's using two V-belt pulleys. So this must be a different machine, but again, similar design. Same setup, you've got synchronous belts keeping the weights in sync. And you can kind of see it better here. You can see the offset weights here, and in fact there are more down there. And you can see the springs these things are mounted on. It's pretty interesting. Professor Dew said that the amount of power required to start these things up, depending on the size, was sometimes so large they had to bring in a tractor trailer that had a generator on it so that you didn't draw too much power from the electric company on startup. Okay? That's what it took. Now that was a bigger machine than this, but you can appreciate in the size of those springs how much motion there would have been and how much weight there would have been that supported it. He also said that companies were bad about not listening to his company that designed the machines, and his company would tell them, look, you're going to have a heck of forces applied at the foundation. You need thicker concrete. You can't just get away with a regular shop floor. You need a significant amount of mass there. They wouldn't listen to him, so Professor Dew's company fulfilled their part of the contract, installed the machine, and shook the whole building. So anyway.
Is that for like tumbling,
I think so. He's described it to me before. They put parts in them, and it was for finishing the parts. Probably cast parts or something like that.
Burrs and whatnot.
Probably, yeah. But it was for processing a whole lot of them at once. You can see another belt here. Now, I bet you haven't seen this in automotive. This is a synchronous belt that has teeth on both sides of the belt. And the reason for that is so you can drive the back side. So you see you've got two shafts here that have to be kept in sync, but they need to rotate opposite one another. These are probably driving shaking weights, I don't know for sure. But you can drive the back side on one and the front side on the other. Now the wrap here, there's obviously a whole lot more wrap on this one than on this one, so I'm really not sure what the application is. If you needed more wrap, you could get it, obviously. You could actually make a longer belt and add an idler in here if you really needed to. But anyway, here's another application where you've got a couple of shaker weights. Why they're going in the same direction, I'm not sure. I would have thought they need to be out of phase, rotating opposite directions, but for whatever reason, they're going in the same direction. And this is just a simple timing belt that keeps the two weights in sync with one another. Were there any belts on this poor machine that we've seen before? There are. There's some V-belts down here. There's a motor down here that's running at high speed to drive a V-belt on a pulley. That pulley is on a shaft that then goes into a right angle gear drive, probably a worm gear set. We'll talk about those later. So that you have a further reduction here on this shaft, and then another reduction through the chain up to the final drive gear, or drive sprocket. Okay. Of course, like we said before, that poor bearing was in need of help. But anybody that would ride that, well, good luck. Here is a setup for testing the tensioning on a V-belt. Okay, so this section here is movable. It's pretty crude, but it would work. You've got some clamps here that you can adjust and adjust the tension on that V-belt. Tensioning V-belts is actually really important. The amount of tension in the belt, if it's too much, there's a couple of problems. Number one, it stresses the belt. Number two, if it's cantilevered shaft, it could bend the shaft. And a lot of times V-belts are used cantilevered on a shaft because you need some way of removing the belt. If you got a shaft that's straddle mounted with bearings, so you've got a pulley in the middle of it, how do you get a belt off of it? Right? You got to go around the bearings, and that's not possible. or not easy. So anyway, too much tension in the belt can certainly break a shaft. Usually it would break it from fatigue. Okay, so getting the right amount of tension is important, because if there's not enough tension, then you can't transmit enough power. Here are some common manufacturers of belts, not just V-belts, but many different types, and I included some links here so that you can use them. These are some of the few that I used when I was designing for Amatrol. Now, belts versus chains. We have terminology, and I expect you to use it properly. This is a sheave or a pulley. You can call it either one. You can't call it a sprocket. You can't call it a wheel. Okay, this is a sheave or a pulley. This is not a gear. This is a sprocket. Okay, so a sprocket is something that a chain rides on. The distance between pins is called the chain pitch. As the chain pitch goes up, the load capability, the load capacity of the chain increases as well. But we'll talk about that in a bit. It's pretty common to use belts and chains for speed reduction. That's really common. Usually you don't get a huge reduction in one chain or one belt, but you do get some. And so frequently you tailor the speed of the machine by slightly changing the pulley ratio or the sprocket ratio. And the reason for this is that electric motors are what's most commonly used for driving industrial machinery, at least that's in a factory. If it's out on a, far away from electricity, then of course it's going to be probably a gasoline engine or a diesel engine of some kind. But electric motors come in standard speeds. So, for example, 1800 RPM is a theoretical standard speed, but a real standard speed is 1725 RPM. There are several others that are common, but the speed required for the driven machine depends on the machine's needs, and so you can tailor the speed of the machine to suit the electric motor driving. Now, speed reduction is something we need to talk about. How do you calculate it? How do you deal with it? Well, the speed ratio is defined as the drive speed divided by the driven speed. Now, that's the same thing as the driven diameter divided by the drive diameter. So think of two pulleys. Think about a small pulley mounted onto an electric motor and a larger pulley on a machine. Is that speed ratio greater than or less than 1? Well, we can figure it out. The driven diameter is larger, right? So the driven pulley is larger. The drive pulley on the motor, I said, was smaller. So that is a speed ratio greater than 1. So speed ratio is greater than 1, slow down, right? Speed ratio is less than 1, speed up. I actually designed a recumbent bicycle once because I was too cheap to go buy one. At that time, recumbent bicycles were about $1,000 a piece. I was fresh out of college and didn't have $1,000. But I had a pile of bike parts, and I thought it'd be neat to make a bike. Why not? I actually built one, welded it up, and I decided I wanted to have not just one, but two 10-speed units in series. So I had two different gear, well, I don't remember how I did it. I don't think I used the front set, just the rear set on each. So I still had two gear shifters, but I had a really wide range because they were one right after another. They were in the series. And so I'd get up to speed on this and start going downhill and switch to an even higher gear and just barely be moving my feet, and the bike would be flying. Of course, the amount of force required was very high. Okay? Can't get around physics. But it was fun riding it, and it was interesting to have this huge gear ratio where it was actually the opposite of what's normal. What's normal in most machines is to have the prime mover turn fairly fast and then the machine move fairly slowly. So you have a gear reduction, or in other words, a speed ratio greater than 1. In my case, of course, my speed ratio was much less than 1 because I didn't have to turn the pedals very fast for the back wheel to spin very fast. Okay. All right, belt velocity. The belt velocity and the chain velocity are important. Usually we're not as worried about chain velocity because chains move at a slower speed than belts. If you end up calculating that you need your chain to move fairly fast, you probably should switch to a belt drive. On the other hand, if you calculate that the belt needs to move fairly slowly, you should probably switch to a chain drive. And we'll talk more about that in just a minute. But the surface speed, or if you were standing on the chain of the belt and being carried along, how fast would you move? That's answered by this equation. All you need is the diameter of either the driven or the drive and its angular speed divided by 2, and that will give you your velocity. You've seen this equation before in dynamics. You probably saw it as V equals omega times R. That's probably what you saw it as. Okay? So just equations that are useful, and again, I'll illustrate these in the context of example problems. Belt speed, speaking of speeds, you don't want the belt to go too fast. It actually can. And so if a belt is moving too fast, you need to figure out a way to slow it down. If you think about the pulley sizes, if you have very large pulleys, then you're going to have fairly large velocities at the outside. Does that make sense? It's kind of like a windmill, right? A windmill turns fairly slowly, but the tip velocity is very high. Okay, in the same way, the larger the pulley is, given 1 RPM, the faster the belt is going to be moving. And so if you end up with a belt velocity that's too high, you can actually decrease both pulley sizes and bring the belt velocity back down. But if the belt is moving more than about 6,500 feet per minute, you get all kinds of problems. There's centrifugal force problems, whipping problems, vibration problems. I guess we do need whips on there after all. I just realized it. Anyway, I guess it stays. Too low, if the belt speed is less than about 1,000 feet per minute, then you're going to have trouble with the belt slipping. Now, here's what students miss most of the time. The purpose of a chain drive or a belt drive is to transmit a certain amount of power. Remember the torque, power, speed equation? How did it go? Power equals torque times speed, right? If we decrease speed, but power has to stay constant, because we still have to transfer 5 horsepower through the drive, what has to happen to the torque? It has to go up. Well, at some point, the belt's going to slip. It won't be able to turn the pulley because the torque requirement's so high, right? So you don't want the belt speed to be too low. How do you overcome that? Well, if you increase the belt speed, you can decrease the required torque for transmitting the same amount of power. Okay? So that's something that's very important. If you calculate that you need a belt to run slower than 1,000 feet per minute, switch to a chain drive. It's easy. Okay? All right, so our guideline for design is that we want to shoot for a belt speed of about 4,000 feet per minute. We'll start there in all of our designs, and that should be a good beginning point. There are many different belt types, as I said. There are actually flat belts. How many people have seen flat belts in operation? You ever get the chance to go out to a farm machinery show, especially where they have some antique machinery, you'll see flat belt drives. Flat belts are older. They're not used as much anymore, mainly because of, well, over long distances they're fairly convenient, but over shorter distances a V-belt is more convenient. A V-belt is designed not to run on the base of it, but on the sides. The sides are supposed to interface with a pulley, and that's where your surface area of contact comes from. It's kind of like taking a flat belt and just folding it up. Okay, that's kind of what it's like. The place where I saw a model of flat belts was interesting. I took my daughter, I think I told you guys, to Minneapolis over the summer. Visited some friends there, and Minneapolis is well known for their mills, their grain mills. So they'll take flour and mill it down there. Well, we visited a grain mill that was no longer in operation, but had been in operation years back. And they had a model of their original plant. It was really cool. Being a mechanical engineer, I loved it. I need to put it into these slides. I took some pictures of it. But the way it worked, they have, the river runs by their plant, okay? It actually feeds into the Ohio. It's not as big as it is here because it hasn't had as much time to collect as many creeks and things. And I think it merges with another major river. I can't remember right now. But anyway, it was still large enough they could drive turbines off of it, kind of like what we do here. But back in the day, they did not use electricity as much. They didn't generate electricity from their vertical axis turbines. I think they said they had 6 turbines, something like that. And each turbine was about so big around, something like that. And the fall was, I want to say 30 feet or something. I don't remember the total fall. But anyway, it was interesting because each one of the turbines was directly coupled to a belt, a flat belt, that then went to the factory, had a right angle gear drive, and actually transmitted power to all the floors of the factory. So it was pretty neat because they had flat belts running all over the place. Now I would have hated to have been somebody that got caught up in one of those flat belts when it was running. That would have been bad. But that is how some farming accidents have happened. In the old days, farmers had, instead of having a PTO off the back of a tractor, they'd have something on the side. You guys probably know more about it than I do if you visited the farm shows, but they'd have something on the side, basically a pulley that you could put a flat belt on and have the power take off. And they can be fairly dangerous, especially if you see some of the videos where guys have built their own wood chopping or wood splitting kinetic devices instead of hydraulics. So you build up some speed essentially with an axe and go right through the wood log. and then drive it off of a flat belt to do it. Anyway, so there are many different types. Flat belts are not all that common anymore, and they're not really used in today's designs. I don't know any modern design that uses a flat belt. There's probably some situation where you use it. I don't know what it is. I don't even know where you buy one. V-belts and their variations are the more common type. Now, in a V-belt, not only do you have the typical wrapped construction, so you've got wrapping all around your thread essentially that reinforces the surfaces, there's also a band in the back near the top that really prevents the belt from changing length significantly, okay? The rubber itself cannot really resist changing length all that much. If the V-belt didn't have this band in the back, you could take it with your hands and stretch it somewhat. But with the banding in the back, there's a name for these, and I can't think of the right word, but basically they're reinforcement, and what they do is prevent that line from stretching or shrinking significantly. You can actually get many different types of materials for this. You can get belts with fiberglass, with Kevlar, with all sorts of things. And depending on your application, there's probably a belt for that, kind of like there's an app for that, right? Now, this is not the only type of V-belt design. Anybody ever seen one designed this way, where there are chunks taken out of it? Why do they do this? Why do they make these cog-type V-belts?
Tighter bend radius.
Tighter bend radius, that's right. If you think about the belt as a beam, the stress is going to be highest at the upper and lower fibers. Well, this section has a lot of reinforcement. This does not. And so as you bend that belt, what can happen is buckling in this area. And so if you basically effectively decrease the thickness of the belt, then the stress is lower and you won't have buckling, and you still have significant surface area for friction engagement with the pulley or with the sheath, whichever you want to call it. You don't want this part of the belt to contact the base of the pulley. You actually want it to ride out of the pulley a little bit. There are also, of course, synchronous belts, and synchronous belts are those that have teeth on them. If you ever had to change the timing belt in your car, you've seen one of these. Some cars, of course, use timing chains. Someday I'll tell you the story of my Toyota that used a chain and caused some problems. I've actually changed the synchronous belt on my Jetta a couple of times. And basically the last time I changed it was because my water pump failed. For whatever reason, the bearings in it failed, and so the water pump was driven off the timing belt, and the shaft just went to the side. Basically, the bearings failed. And so instead of the water pump riding straight, the whole shaft was angled. And all of a sudden, I was driving home, and I heard this horrible noise under the hood, and stopped immediately, at a gas station. Fortunately, I was, a quarter of a block away from one, and saw water just pouring out of the engine, and antifreeze as well. And I realized, well, I think the water pump went out, and sure enough, that's what it was. So when that happens, you don't reuse the belt that's been damaged. You put a new one in, and that's what I did. So anyway, these belts also have reinforcement because, again, they're just rubber and they can stretch easily. There are poly-ribbed belts. You've probably seen this for your serpentine belt on your car, right? So it's essentially where you've got a lot more surface area because there's so many sides here that add up to surface area to contact and hopefully not slip. Then there are V-band belts. These are like having V-belts but attached together. They're frequently smaller but not as small as a poly-rib. And there's double angle V-belts. Why do you think you'd want a double angle V-belt?
Just in case you have
Different directions, so you can drive the back side of it, right? You wouldn't want to try to drive anything with this. You wouldn't want to try to transmit power with this surface. It's too slick. But this type of belt allows the front side and back side to transmit power. So as I said, you want the V-belt, for example, to ride a little bit out of the groove and not contact the bottom of the sheath. Now, there's a bunch of terms here. The groove angle, the belt ride out is how much it is above the pulley. The pitch diameter. The pitch diameter is really important. The pitch diameter essentially is something that allows you to relate the gear ratio of the belt. Because you think about it, you've got all these different diameters. The center line of the pulley is down here somewhere. So you've got all these different radii. Which one is the right radii? Which one is, determines the effective gear ratio? Well, the pitch diameter is just the point where the belt, how can I explain this? It's the diameter you use for calculating ratios. Does that make sense? The actual pulley is going to be a little bigger than that. So if you're If you buy a nominal 6-inch pulley, it's going to have a little bit more on it because the 6-inch pulley is going to be the pitch diameter, at least it should. Now, if you buy it at a mom and pop shop, who knows what you get, or if you get.
So the pitch diameter is basically where the banding would be?
Not necessarily. It's usually a little bit below the banding. And the reason is because there's enough stiffness in the rest of this material that the pitch point moves down a little bit away from the banding. But it's close to the banding because the banding is the point where it doesn't stretch. I don't think I did a good job of explaining that, but hopefully you guys understand. They're pretty straightforward and simple. All right, so belt tension. You have to have enough belt tension to prevent slip. You don't want to have too much, as we said. And you follow the manufacturer's recommendations, and you should check it because belts do stretch. Chains stretch as well, something you should know. But, and of course, as we discovered last time, sometimes the design of the machine can cause the chain to stretch, and you should avoid that in your design. But anyway, the way this is usually checked is with a gauge. This is basically a tool that has a spring on it, and you just push down until you get a known deflection of a certain amount or a known force, and then measure the deflection. So it's a deflection of belt versus force relationship that you shoot for. And again, usually you will just follow whatever the belt manufacturer's recommendations are, or the machine manufacturer. But if you're the one making the machine or designing it, then you have to get Gates or whoever to help you know how much tension is appropriate for the belt so that the belt can last. Now, like I said, when we were talking about shafts, the belts have a slack side and a tight side. In this case, let's see, it looks like that this would be the driving sheave, so it's turning clockwise and pulling on the belt, but the slack side still has significant force in it. Now, we're going to approach this from the belt's standpoint now instead of a shaft or a pulley standpoint, and think about what's happening here. As the belt goes around the pulley, it gets bent. Think of it as a beam that's going to be bent, right? The farther it's bent, the more strain, in other words, the higher the stress in the material. And the higher the stress, the more the belt is damaged each revolution, okay? So really, the belt is damaged the most on the smaller pulleys, not as much on the larger pulleys because it's bent around a smaller radius. So what this leads to is a recommendation on the minimum size of pulley that's practical. Okay, you don't want to bend too much. And of course, the smaller the sheaves, the lower the belt life is going to be. And so if you need a machine to last a long time, one thing you can do is simply upsize your pulleys so that the belt lasts longer. Okay, because the farther you are from a tight radius, the more the belt is going to like it. How do we select V-belts? This is just one way, but this is a very common way. You look up design horsepower, okay, and speed of rotation. Where they intersect, you get a recommended belt size. This is one of the simplest ways, but this is very common. Okay? Now, design horsepower is not just the power output of the prime mover. Let's take a simple example. Let's say you've got an electric motor that's putting out 5 horsepower. Okay? The number you use here on this axis is not 5 horsepower. It's the input power, 5 horsepower, multiplied by a service factor. See, here's the thing. If you have a smooth electric motor, there's not going to be many torque spikes that get transmitted through the belt. But if you have a single cylinder piston engine, every time the piston comes around, there's going to be this hard twist on the crankshaft, and that's going to be transmitted through to the V-belt. And so you have to have a service factor, but that's not the only thing. There are also varying loads from the machine. So if you look on, I think I've got a reference there, page 245 should be the right one. Page 245 is worth a tab in the belts and chains chapter. And of course you see this V-belt selection chart in the text. That's where I got it from. But one thing I don't have in my slides is the table below it. The table below it is very useful because that table gives you the design factor, or the service factor, I'm sorry. It gives you the service factor. So let's take some applications. And what application can you think of for a V-belt?
Drill press.
Drill press. Okay, so on a drill press, what's the driving or prime mover? What is it? It's an electric motor. Okay. Well, let's look up electric motors. Driver types. Well, let's see. We've got AC motors normal wound, DC motors shunt wound, and engines multiple cylinder. Or we have AC motors high torque, DC motors series wound or compound wound, and engines 4-cylinder or less. Essentially, the right-hand side of this table is rougher drivers. The left-hand side is smoother drivers. In the case of a drill press, I imagine the motor is probably simply a normal torque AC motor. So I think we're in the left-hand side of this table for that application. What about the driven machine? Well, let's see. The driven machine type, we've got smooth loaders like agitators, light conveyors, centrifugal pumps, fans, blowers under 10 horsepower, light shock, generators, machine tool mixers. I think that's supposed to be machine tools / mix or comma mixers, fans and blowers over 10 horsepower, gravel conveyors. So it sounds to me like we've got a machine tool. It's a drill press. So our service factor depends now. It's either going to be 1.1, 1.2, or 1.3. It depends on how many hours a day this drill press is used. So if this drill press is used for 2 shifts, 2 8-hour shifts a day, then the service factor would be 1.3. You guys see that? Would it be wrong to assume that you've got an AC high torque motor and choose 1.4 as your service factor? Would that be wrong? You could make an argument for it. I don't know. The drill presses use normal torque AC motors. They could be high torque AC motors. So there's some flexibility here. I'm not going to tell you you're wrong about your service factor unless you're just really way off. Okay? And on an exam or any homework where I specify very clearly and it matches exactly what's in this table, well then pick the one that it matches. Right? Then there's no need for any judgment. Okay. So anyway, we have a service factor of 1.3, multiply that by 5. Let's take that as an example, why not? So 5 times 1.3 would be what? I can't think. 5 plus it's 1. 6.5. So our design horsepower is about halfway between 6 and 7. And what about a speed? Well, it doesn't really matter what speed we choose. We're probably going to end up with a 3V type belt. Okay, unless we're down here at a very low speed. How come at lower speeds the belts are bigger?
Probably more torque.
More torque, right? So more force in the belt, so you need a larger cross section. And in fact, speaking of cross sections, look at the facing page, page 244, and even 243, and you will see some standard V-belt sections. If you can go back one page and see that we've got quite a few. And they should be to scale. They should be printed to scale. We're pretty close. Synchronous belts use a very similar procedure, but here the power transmission relies on teeth instead of relying on friction. We're not going to size any synchronous belts in this class. In fact, the methods that I'm showing you here, you may not use at all. When you need a V-belt, you'll go to the manufacturer from whom you hope to buy the V-belt and use their selection criteria. And most of it will probably be very similar to this. Chain, on the other hand, is classified by pitch. So that's just the spacing of the links. And here's some common manufacturers of both sprocket and chain. Now, what you see on your bicycle is basically standard roller chain. Well, it's not exactly standard, but it looks like standard roller chain. There are also 2-strand standard roller chain. You can also get 3, 4, and more strands. And they're tied together. Heavy series has thicker link plates on the side than standard. So these heavy series can take more load. Okay? Double pitch chain and double pitch conveyor chain are chain that are made so that as they go around, they don't impact every sprocket tooth every time they go around. Okay, so it helps reduce wear on sprockets to have double pitch chain. So these are really common on conveyors, for example. By the way, one thing to note with this double pitch chain, if you have an even number of sprocket teeth with a double pitch chain, that's a bad idea. All right? Because every other tooth is going to be hit every time. You want an odd number of sprocket teeth if you're going to use these. So anyway, how do chains fail? Well, usually what happens, well, one thing that can happen is fatigue of the link plates. If you think about what's going on here, as the chain comes around on the tight side, the chain is pulled, right? There's a significant load in the chain. And then it goes around to the slack side where that tension is released. And so this is a fully reversed, well, not fully reversed, this is a cyclic load that's applied. It would be fully reversed if you compressed it on the other side. But you can't push a chain just like you can't push a rope. Well, you can push a chain, actually. Have you guys seen the garage door openers that don't have a chain loop? Instead they have a length of chain that's captive inside of basically aluminum, can't think of the name of it, aluminum channel basically. So you can push a chain, but you got a guide or a link to do it. And it helps to have some weight pulling at the other end. So anyway, another thing that can happen is that the chain can impact on the teeth as they come around. If it's moving fast enough, the impact is significant. And that can cause wear of both the rollers, which are these elements on the chain, and the teeth themselves. There can also be galling of the pins and bushing. See, there are pins that run through each of these, and the rollers should be able to roll. So there's essentially, there's not bearings inside of it, but it's supposed to be lubricated so that they can roll. Well, if there's a high enough force on one particular roller, what will happen is the pin inside will have too much load. You can actually transfer material from one to the other, and that's called galling. Yes?
I know there's a couple others. You can drop a screw into the chain, and when it goes around the sprocket, it destroys the sprocket.
Another method of, yeah, so foreign objects.
Alignment is a big problem with the chain.
Yeah, so you're talking about abuses of the chain rather than normal application. These are failures under normal, proper operation. You're right though, foreign objects can destroy it, and if you don't line these up. And alignment actually is really important in belts. It's actually easy for a belt to be misaligned. I've got two different backhoes, one that runs and one that doesn't. So I've basically got a scrap metal pile and a backhoe. It's probably going to be a scrap metal pile before it's all said and done. But anyway, this backhoe that I've got, it's a Case 530CK. And when I bought it, it had a generator on it, and that generator didn't work very well. So it wouldn't charge the battery. So I said to heck with it, took it off, and bought myself a cheap alternator, because you can get an alternator, a one-wire alternator, fairly inexpensive. Put it on, did a little bit of electrical work. Well, the problem was that I don't know what the deal was with the original generator that was on the thing, but the pulley for the generator and the pulley on the engine were offset literally by probably 3/4 of an inch. There was that much offset. You could see it just looking at it from the side. And so when I put the alternator on instead, I modified the bracket and actually made my own custom bracket to move the alternator forward so that the pulleys lined up. But lining up, speaking of problems and installing things correctly, lining up pulleys is very important and getting them to the same level so the belt's not wobbling back and forth and wearing incorrectly. Lining up chains is very important. Lining up shafts is important. There are systems made just for lining up shafts. If you got two shafts and you're going to hard couple them together, you can't have any angular or offset misalignment. It won't work. And in fact, even if there's a soft coupling between the two, the more aligned those two shafts can be, the longer the machine will run without maintenance and the less wear and tear on the coupling. And so you can actually buy tools that are basically laser alignment tools where you clamp two pieces, one on one shaft, one onto the other, and basically bounce a laser off, and it tells you what the misalignment is, so you can adjust one shaft to the other and make the machine run longer. So that was a good discussion point. Anything else you guys wanted to mention here? Okay, so it's very important to keep chain drives lubricated, and there are basically three different ways to do this. One is a drip feed lubrication system, another is a shallow bath or dip lubrication, and then there's actually an oil stream lubrication. The difference between these different things, this is kind of like what you do with your bicycle, where you squirt some oil on the chain every now and then. Well, there are automatic systems for dripping oil onto the chain in industrial applications. That's possible, and that may be completely acceptable. The oil bath is a little bit better, and you can put the chain under a little bit more load because you know that the chain is going to be bathed in oil. But what is the best is oil stream lubrication, where basically you have a pump that's pumping oil onto the chain continuously. And basically what we're going to do is the order goes like this, where you can put more and more and more load on the chain without the chain failing. Okay. All right. I'm going to stop the video at this point. We've got one or two students that asked me to video today's class as well, so I'm going to post it. The reason I'm stopping is because I'm about to show a video, and YouTube will flag my video because the other video is playing in it if I do it. But you can go to the chain, belts and chains learning module and click on the various videos that I'm going to show here. There's bike chains, how it's made, industrial roller chain, how it's made, and I'm going to show you the original fast Volkswagen belt chain. So if you're watching this video, you'll want to go check those out on Blackboard. And then that'll be the end of the class.